Okay, so hopefully somebody online can give Nicholas a thumbs up to say that they're hearing me okay. As you'll hear, because we want to be able to accommodate people both online and also in the room with less good hearing, we do use microphones. So for those of you who haven't been before, that's something that's quite important, though I might turn the gain down a little bit in a minute. Very much welcome to the cafe. Very nice to see everybody. I can see a few new faces I haven't seen or perhaps only seen online, which is really, really good. And just to say that there's some quite small writing on the slides today. So we're sharing the whole thing on the computer so everyone can see. And we've also got 6 sets of the printouts of the slides on the tables that people can have a look at to make sure that they can actually read all the details of particular things, which hopefully will work. As usual, we're recording, so we're streaming live and then we record, and in a day or so I put it up online. Just check it for anything that needs editing out. And they'll go onto the private YouTube channels that we use. So I have a private playlist for 2023, and anybody who's on our mailing list or who asks me for the link can have it. We just ask it doesn't get broadcast on social media so as to avoid any amount of boring trolling. Welcome to the cafe. And this is the venue we've now used since December. We're still kind of adjusting it and getting it right. Slightly new layout tonight. Would very much like to know from the regulars if they prefer it or not. To explain the format of the cafe for those who haven't come before, we start with a short talk from the speaker, and then we have a little break straight after that, just long enough for a few minutes to everybody to refill their glasses and get a few more snacks in the room. Just to say that the cafe runs on donations. Very kindly, Pharmacology are not charging us, but as you can see, we've had to bring our own speaker system, microphones, screen, projector and things, so any donations are very welcome. There's a lovely felt black hat at the back, which you can throw any spare change into, and that will help cover the cost of the food and the drink as well. After the break, we have a longer discussion. In the room, you're very welcome just to catch my eye, give me a wave, and then say or ask whatever you want to. And anybody online, if you could use the chat, please, rather than unmuting yourselves, keep muted, and use the chat, and we will field questions from that as well, and comments. So I'm absolutely delighted tonight to introduce Kathy Wells, who's kindly come from Reading at the end of her very long day. Kathy actually spent, I think it's 21 years as a maths teacher. Scary lady. And then very sensibly decided to come back into academia, did her doctorate for which she won a prize, she and her team won a prize, and is now working for the Walker Interdisciplinary Climate Research Institute in Reading, which she will tell you more about if anybody's interested. The talk will be short, there's plenty of opportunity for her to expand on anything she's just touched on lightly. And so basically over to you, Kathy.
Thank you very much. Okay, what I'd like to share with you is very much from my PhD work. It's research on how we can reduce carbon dioxide emissions by just rerouting flights across the Atlantic. Up until now, there's been really poor situational awareness across this stretch of airspace. And that means that aircraft have had to use these tracks. These are organised by air navigation service providers. In England, we've got a group called NATS, and they do the tracks going over from England to America. In the other side of the Atlantic, we've got Nav Canada doing the same in reverse. And the reason we've needed these tracks is because planes haven't known where other aircraft are, and the air traffic controllers haven't been able to work out where the aircraft are unless there's a definite track that they're following. These are spaced out by 40 nautical miles going laterally, and the planes along the tracks, they have to keep 10 minutes away from each other, which is about 80 kilometers. What you can see in this top picture are the tracks going from America, from John F. Kennedy Airport in New York, over to London Heathrow. And you can see also in white, there's this great circle route, which is the shortest distance track between the two airports, so going around the sphere. You'll notice that these tracks all seem to head quite close to the Great Circle route, whereas when we start going west, we've got all the tracks trying to avoid that Great Circle route, which might seem counterintuitive, but some of you probably know that the prevailing winds across that stretch of the North Atlantic, we have the jet stream, which 99% of the time is flowing east. So So planes can go along that shortest route, but if the westbound planes try to go along there, they get a lot of headwinds, and it would cause them problems with both time and the amount of fuel they'd use. Oh, this is not appearing, so. I'm just going to see whether this will then, yeah, okay, we're back to. So what we're going to do today is just look at why are we going to try and change this organised track system. It's been going for 60 years. Surely, if it's been working all that time, it's not worth changing. There are three ways we're going to look at rerouting very briefly. The first is time minimal. The second is using fixed time trajectories, but then trying to minimise fuel. And the last one is opening time up again, making it free time, but still trying to minimise fuel. And that uses three different kinds of optimal control solution. The first one is via Pontryaggin's minimum principle, so it's an indirect method. The second one is a direct method, which looks at a gradient descent version of just trying to minimise a fuel use. And the last one, we use dynamic programming. After that, we'll look at where this research could go in the future. Why do we need to do this? Well, commercial aviation at the moment is responsible every year for only just fewer emissions than the whole of Japan. By 2050, the United Nations Framework Convention for Climate Change would like commercial aviation to be net zero. It's going to be very difficult to do that. The European Union has asked to drop emissions by 55% by 2030. Again, the only way that's going to happen is if we use offsetting in a major way. And offsetting is obviously not the same as not creating the carbon dioxide in the first place. We could just ground all the planes, just take them out of the air. But actually, we rely on aircraft, obviously, for freight, for passengers. It probably won't surprise you to know that commercial aviation contributes massively to global GDP. What you might not have realised is that we also rely on those flights for weather forecasts. And during COVID, when 75% of the global fleet was grounded, there was actually a significant decrease in the skill level of weather forecasting. So what could we do about this? We could change aeroplanes. They have actually changed quite a lot in the last 30 years already, so the only thing that's left to us is a major redesign. And that's something Airbus have been looking at. These are both hydrogen-fueled planes that they're starting to design and starting to work on. We could try just to load a lot more passengers onto the same flight. That would make it nice and efficient. Our problem there is, if you look at on here, this shows you the most efficient flight in terms of fuel per person. This company are the least efficient. Well, the most efficient have gone bust over COVID because they didn't have the money to keep going. The least efficient are British Airways, and that's because they sell space at a premium, and that's their business model. So to tell them to shove more people on board is not going to go down too well. We could start looking at flocks of aircraft, and in fact that's something that's already been really experimented with by Airbus. So they've sent 2 Airbus aircraft out from Paris to Montreal, 3 kilometres away from each other, and that meant that the back aircraft could actually slipstream the front aircraft. And that meant that they saved about 5% of fuel, which is great as long as you get the aircraft together, either on the ground or in the air, and neither of them has a problem once they're up there. So there's still a lot of research that we need to put into what happens if there's a delay, what happens if there's a technical issue. One of the key solutions that people have looked at, certainly from the International Civil Aviation Organization, is to do with sustainable aircraft fuel. However, we'd first of all have to find space to grow the necessary crops to make the fuel. We could do this. This saltwort will grow in brackish water where we couldn't grow food crops. But the other problem is actually producing it. Even with the research that's going on now, by 2050, we're only going to produce 1/3 of what we actually need. Our idea is therefore to try and have some kind of short-term, low-risk, nice inexpensive solution that will just tide us over until all of that technology can come online. Why are we doing this now? Well, we now have the Ariane ring of 66 low Earth orbit satellites, and that means we have 100% global coverage suddenly. So the aircraft know where other aircraft are, and the air traffic controllers know where everyone is at any point. That means we can move to something called trajectory-based operations. This is where we plan every route to exploit the atmospheric conditions that a plane will actually meet as it moves across the North Atlantic. We just need to ensure that whilst we're trying to reduce these emissions, we're not taking too much time, because airlines do have a certain schedule that they need to stick to. We're going to use optimal control theory. If you think about all of control theory, we're just in this top corner up here. So we're going to be looking at indirect, as I said, Pontryaggin's minimum principle, direct, which is a gradient descent function, and dynamic programming, where we start using Hamilton-Jacobi-Bellman equations. What you can see in this diagram, this is the flow of that jet stream. Here's John F. Kennedy Airport, here's London Heathrow, and those are all the days from the 1st of December 2019 to the 29th of February 2020. And because it's nice and slowly evolving, that means we've got time to actually create these routes 2 or 3 days in advance. Our method is that we're going to go between just those 2 airports I mentioned. We're going to be looking purely at that one winter period. Our winds are coming from reanalysis data, so it's a deterministic wind field showing us zonal and meridional winds. We're going to keep to a constant altitude. We've chosen 34,000 feet, which is about 250 hectopascals, and that's because that's quite a standard cruise altitude. We're also going to keep the airspeed the same across each trajectory, but look at different airspeeds for different trajectories. One of the reasons that it's good to do both of those things is that then we can use air distance as a metric to test efficiency. And air distance is how far the plane flies relative to the air around it, not relative to the ground below. Air distance is a great metric because it means both the fuel that's being burnt and the emissions that we're creating by burning the fuel, those are both directly proportional to that air distance. And we can use that to measure what our routes are doing, but also what a route along each of those tracks would do. Our spherical system is based on longitude and latitude. We've got a heading angle, which is just measured from due east round anti-clockwise. Your zonal winds are coming west to east. Meridional winds are going south to north in this system. And that leads us into the optimal control problem. You'll see lots of these this evening, so you'll get used to them. The parameter is time, and all we know is that we start at 0 and we don't go backwards. We have got our state variables of longitude and latitude, and we're actually going to set some boundary conditions saying we're going to depart from the departure airport. We're not going to arrive at the destination airport. It's not because we're Ryanair, it's because we're going to put a non-linear constraint on all of our routes and only accept ones that have a certain radius. Our control variable is that heading angle, so that's what we're going to change to make our routes more efficient. And you can see the dynamical system is just the rate of change of longitude with time and the rate of change of latitude with time. And that really is just the zonal component of the airspeed added to the zonal winds, or the meridional component of the airspeed added to the meridional winds. And the factor underneath, that's purely mapping from a flat map onto a sphere. Our cost functional is time, because that's all we care about. We just want to minimize time for this particular model. When we look at this, we've got our dynamical system, the first 2 rows, but then we get this 3rd row, which is the rate of change of heading angle with time. Now that is created using Pontryaggin's minimum principle. And I have 8 really lovely slides that if you want to see them later, I'll be more than happy to go through with you. But until that time, we'll accept that we now know what's happening with the heading angle and time because we've applied Pontryaggin's minimum principle. This now means we can use an Euler forward step. So if we know what the longitude is and we know how it's changing with time and we know what our time step is, we've got a numerical system, we can work out where our next longitude is. Same with latitude, same with heading angle, where that wind expression is actually a lot of stuff. But all of these little gradients, we have to find those numerically because obviously we don't know the rate of change of zonal wind with longitude and latitude or meridional wind. Once we've stepped across with these, the only slight issue is we don't know our initial heading angle, but we in fact used a bisection method in order to home in on the perfect heading angle each time. Here are some results now. You can see this line in dark blue. This is our optimized for wind route. In orange, you've got the air distance that would be taken by an aircraft flying along the Great Circle route, and in this case it's in amongst all those other tracks. All the other lines, that's what air distance an aircraft is covering when it's going along one of those organised track structure tracks. And you can see that in every instance we're using a lot less air distance, so it's a lot more efficient. We could then average that for every single day, because what you just saw a minute ago was just one day example. We could average for every day, and that would give us the green line and the pink line, telling us what savings we're making in terms of air distance. However, not all of those tracks are used the same amount. So what we did was we got some data from NATS, who told us how many planes actually flew along each of those tracks each day. So we were able to then work out a weighted average, and that's what you can see in the blue and the red lines. That's just showing us exactly the savings that would have been made in that winter period. 240 meters per second tends to be quite a standard cruise airspeed, so if we home in on that one, it allows us to work out percentage improvement. What you can see in this diagram are our optimised for wind routes every single day of that winter period, and those are in red and blue. In pink and green, you can see just the most efficient track on every day. And you can see that sometimes those lie quite close together, sometimes they lie a bit further apart. But you've got to remember that there are several other tracks that are less efficient every day as well. So if we compare to the very least efficient track, we can make a 16.4% improvement, which is enormous. But compared with the best track, it's more of a sort of 1% improvement. But over that weighted average, we're 2.5% going eastbound and 1.7% going westbound. And that would have prevented 6.7 million kilograms of carbon dioxide emissions over that one winter period. So that's just using time minimal. What we thought then was, what if we fixed time and started minimising the fuel, so that then airlines can schedule really easily and planes are not being stacked, because once you're stacked, you're flying at a speed that's really not very efficient, you're flying at an altitude that's really not very efficient. This meant we had to have a fuel burn function, and this is something that Paul and Schumann have published recently. G is not gravity, it's actually the rate of change of the fuel with time. We've got the weight of the aircraft, we've got the airspeed, the lower calorific value of the kerosene, the lift to drag ratio, and also this E to naught. This is telling us about the overall efficiency of the propulsion system. Now, to work all that out, we now need to start looking at aircraft parameters. So we need to look at different models of aircraft. We need to look at some of the international standard atmosphere. We also suddenly need temperature cropping in here. And that, again, came from the reanalysis data set. So we've got a whole map of temperatures to go with our maps of winds. Our method assumptions are pretty much the same, but you may have spotted that we've now got fixed times, and those are based on some of the results we got from the time minimal. So we could say that on every day the plane can definitely get there. We're going to change the mass of the aircraft now. Mass didn't really come into it on the time minimal approach, but it does for the fuel minimal. And we're using that new fuel burn function. This looks really similar. Hopefully you've spotted the difference, or several differences. We've stuck our time as definitely being a particular finish, and we've also got a third state variable, which is our mass. So when we look at our boundary conditions, we have our mass of departure. We're still in this case in optimal control problem 2, just using the heading angle. But what we then did was look at what happened if we put in our airspeed as well. So we want to control both of those and see if it makes a difference. So we can justify maybe bringing that airspeed into the equation later on. That means that the dynamical systems, very similar to what we had before, but we've now got our rate of change of mass with time, which is to do with our fuel burn. And we've also got our cost functionals based on that fuel burn. What we saw in our results is that the air speeds did change depending on what the winds were like each day. And if you've got a really nice route with lots of wind vectors going exactly where you want to go, an aeroplane will use lower air speeds, but also a larger variety of air speeds. So this aircraft on the 26th of January, it actually cruised into the airport going quite slowly on our simulation. If you've got vectors that aren't lining up so nicely, you're having to stay at the much higher end of air speeds because you're having to fight against headwinds. Overall, everyday savings could be made by altering both the airspeed and the heading angle, and those differed very much depending on what sort of wind field you had each day. And that gave 723,000 kilograms of extra carbon dioxide emission savings by having that second control variable. What this then told us was that for our third system, we should use both those controls. We should use heading angle and airspeed. We opened up the free time because there are now a few schemes where planes can land as soon as they get to an airport. So if you're coming into London Heathrow and you're coming in a bit too early, but nothing's taking off, they will now land you on the takeoff runway. So there are various schemes like that that have started to happen where air traffic control is becoming a lot more flexible. It's our old friend again. Very similar to what we had before, we've just opened up our time. If we look at a time minimal, just for comparative purposes, it just means we're going to take off that state variable of mass, but this time we're going to keep our two control variables. Funnily enough, the airspeed isn't much of a control variable for time minimal because it'll always stick you right at the top possible airspeed, but it was worth looking to see what was going to happen. In some ways, it's a check on the actual coding that we were doing with the Hamilton-Jacobi-Bellman equation. Is that not going to work now? Every now and again, it gets really upset. There we go. So, very similar dynamical system. Fuel burn, again, is what we're adding up, unless we're doing time minimal, at which point we go back to adding up time. From there, we're using dynamic programming, so we have something called a value function. The value function tells us how useful every set of our states is. So if we've got a big grid of our longitudes, latitudes, and our masses, because there are three states, at every sort of grid intersection point, we can find a value that says how useful is it flying through here to get from the departure to the destination airport. And we can do that for a time minimal version and for a fuel minimal version. Basically, we create the big grid, we set all the values to 1 apart from the target, which we set to 0, and then we update using an iterative function. So we're actually using a semi-Lagrangian method to solve our value function. This looks a bit like this. So you start with lots of 1s, and gradually those values propagate out until you've got a grid that tells you, if I started at the departure airport, if I look at every single set of controls, what's going to get me to the lowest value point? And you do that all the way across until you get to your destination. We compared it with actual data because it's always really useful to compare with real flights. So we were just looking at the cruise phase, not looking at takeoff or landing. And we had 4 different airlines to play with, and we took data from Flight Radar 24. We had 3,100 flights, just over that we were interested in. And what we found was, this is going eastbound, we're using significantly less fuel, both on a student's t-test, and you can see with the notched box and whisker as well, using significantly less fuel than the actual flights. The time minimal is not using significantly less. When we look at the amount of time we're using, we're not actually using significantly more time. Obviously, time minimal is doing the best, because that's what it's designed to do. When you look at the airspeed, you can see what's happening with the fuel minimization, because obviously time minimal is stuck at the maximum speed it was allowed to get to, but we're using significantly lower airspeeds than the actual flights are using. So that means that by changing the heading angle, we're able to slow down, and in slowing down, because we've got the right winds, we're not actually having a much longer duration flight. So we've managed to hit the sweet spot of not taking too much longer, but using significantly less fuel. And we had the same sort of results going westbound, just not quite as obvious some of the savings, still significant, but not quite so obvious. And we can look at different airlines as well. So we can split these up, and you can see that Virgin likes to get everywhere fast, but burn a lot of fuel. Most of the other airlines would actually save time and fuel. If we look at flying east, then Virgin, just by dropping 1% of their time, could save 5.5% of their fuel. What this tells us, well, we can save over 5 million kilograms of fuel, which is always nice for the airlines. They really like a solution that's a win-win. That means 16.6 million kilograms of carbon dioxide. So that's a huge amount. It's really hard to picture that. So that's the same amount. Ooh, okay. Oh, no, I'm going to have to do it this way. Let's just see. Okay. It's the same amount that about 1,300 residents from the UK would emit in 1 year, which is the same amount of people as would fit at the bottom of the Blackpool Tower. Or it's the same as just under 16,000 average people in Pakistan will emit in a year. And that's the number of people it would take to fill the Rawalpindi Cricket Club, including the people who like to stand around the boundary. So it's a huge amount of carbon dioxide that we could be saving. Our conclusions are, yes, we can definitely reduce carbon dioxide emissions by rerouting, and using the airspeed is going to be useful as well. So actually trying to factor that into route planning. Probably the nicest conclusion of this work was actually that after we finished the time minimal paper, we talked to NATS about it, and they were really interested in the work we'd done, and they decided to they cited our work in their decision to change the organised track structure and start doing some experimenting with it. And actually from March last year, they've taken the organised track structure out up to 33,000 feet, and they're sort of trying to negotiate with Nav Canada at the moment about whether they can take out more tracks further up, because we now have the technology to be able to fly planes closer, and we've shown that it's worth doing that. So where could this go to in future? We quite like to try and control some cruise altitude, because everything's been fixed altitude so far. It would also be really nice to include the climb and descent phases, although on a transatlantic flight, that's 2.5% of your flight, so it's not a massive change, but it would be useful. We haven't looked at convection and things like supersaturated icy regions. Those are things we could block off on our grid when we do Hamilton, Jacobi, Bellman. So we could actually start doing that, but it would mean having nowcasts and having much finer resolution forecasts. The other thing that would be useful would be maybe training some neural networks, because then when we work out these routes, it maybe takes an hour to get a route coming through, sometimes less than that, depending on how awkward the wind field is. If we've done all that prior to actually giving the information to the pilot, and they can just use a nice system on a neural network that says, okay, when this wind field comes up, this is the way to fly, then that will mean that it becomes a lot easier in an operational sense. So that's all of the work that I was going to share with you about rerouting flights, and I'd be very happy to take questions, but I think, do you have a system of wine first, then questions?
Thank you, Kathy. Yeah, we absolutely do. So we're going to take about 5 minutes. Hang on a minute. Okay. I was going to say thank you first, and then we can clap. It'll take about 5 minutes. If Nick can stop recording, that would be fabulous. Just pause. And then we'll see you. Okay, so I think we'll get going again. As usual, we've got people who are putting in comments and questions in the chat. Hopefully we've got people in the room. I have to say, I don't know if I was the only one. I was sitting there going, I did maths quite a long way past A-level, and quite a lot of that was just going whoosh over my head. This sounds like terribly clever mathematics. Is it something we could understand a bit of or not?
Well, hopefully, is that working? I'm not sure that's working. There we go. I think it's on. Try? Yeah. See if it's not. Is that on? I can hear it. Oh, hang on. Okay. Maybe it is. Yeah, it sounds like it is now. That's fine. I think the basics are not actually too difficult. That whole idea of we're just taking the zonal component of the airspeed and the zonal winds and the meridional component and the meridional winds. So that first sort of stage of the dynamical system is quite straightforward. If we then try and solve it in an indirect method, we're first having to optimize and then we're discretizing. So we're first of all trying to get an optimal system, and that's where we get that rate of change of heading angle with time. Then we're discretizing by putting time steps, and that's where we use the Euler forward step. When you use the gradient descent method, that works the opposite way around, so that's a direct method. So we discretize first, We put time steps in first, and then we say, for all of these little time steps, what's the optimal value that we're getting? And you're just trying lots and lots of different values, and that's quite a brute force way of doing it. So it's using a global search around an F-min-con search, if anyone's into MATLAB. So it's not so much the optimal control problem that's difficult, it's solving it.
And just to talk about those terms you're using, which are more to do with the aircraft, just so we understand them. So zonal, meridional, heading, I think I understand, is the angle relative to north direction.
The zonal winds are going from one side to the other, sort of, think of them as horizontal almost. Yeah. If you were taking a point, you're taking a point around a severe, you've got a whole horizontal system, in fact, but your x-axis is kind of your zonal winds.
Like a belt going around the Earth.
Okay. Yeah, your y-axis is going perpendicular to that, so they're both belts going around the Earth, just perpendicular to each other. Your heading angle in this case, we went from due east anti-clockwise, and the reason for that is that Zermelo, who was the first person to come up with some of these ideas back in the 1930s, that was how he defined the angle. So rather than going for a bearing, most routing algorithms will work from that due east round anti-clockwise.
Thank you. And this sounds like this MATX in a way has been quite specifically developed for movement around the Earth. Is that the case, or can you use it for other things?
Well, optimal control has masses of different areas that it can be used for. It's used a lot in engineering, it's used a lot in processes in factories. Most of the time when it's used in engineering, it tends to be because there's a nice analytical function. And if you've got an analytical function, then you don't need to do all the numerical methods that we were having to use. I did one version of this where I had a nice analytical wind field just to test some things out on it, and it was beautiful, everything fell out. But it's not quite the same when you get to real life. So when you have a complex wind field, it makes it very different.
And presumably it's used also for things like delivering exactly the right amount of baked beans to the supermarket and things like that as well. So where you've got lots of variables, including human behaviour.
What you don't want is too many variables, in fact, for this. You want to have a number of states, and those states must get from an initial state to a final state using controls, and the controls give you the trajectory, and you optimize that trajectory. If you have lots more states or lots more controls, you have what we call the curse of dimensionality. And because you're trying all the different states with all the different combinations of controls, one extra state or one extra control can lead you to a massive increase in the amount of calculations you have to do. And it did overload MATLAB when I tried to include altitude. So MATLAB did say, please stop now. So I did.
Thank you very much. Have we got anything in the room? Let's go over here first. Let me come around. We're going to ask people to just make sure they speak through the microphone, if that's okay.
On a practical level,
yeah.
Who and where is doing the calculations, and how does that get into the pilots or the aeroplane, and how does it actually work between where it's calculated and making the plane go in the right place?
So at the moment there are 4 companies that design routes, and all the airlines will talk to those companies before they have to talk to NATS or NAV Canada, and they will create a preferred routing message, and that preferred routing message will go to NATS and NAV Canada, and they will try to work out with their tracks what the best track for that route is. Once they have decided where everyone has to fly, they will send back to the airlines the route that they have to fly along, and then the pilots will have to program into their onboard consoles where they need to be, and they can also put airspeeds in as they go. What we've tried to do here is keep the time step to a reasonable amount. So we did about a 2-minute time step when we got to the Hamilton-Jacobi-Bellman version, because that tends to be where planes at the moment are changing heading or changing airspeed. It doesn't tend to be a continuous process. So it is very much using the onboard controls to be able to do that, but you'd have to look a bit more at the thrust. So we've sort of done an instantaneous airspeed change. There would have to be a bit more looking at the rate of change of the airspeed with time in order to be able to work out how the thrust would kick in. But at the moment, when you drive your car, you would tend to accelerate and say, I want to be doing this speed here and that speed there. And acceleration is a very small amount compared to the part you're driving. So I don't think it would be too difficult to sort of put that into the system.
I'll just talk up. So how do you quantify the risk? Is it Max that does that, or did you have a conversation about that?
Can you just repeat the question?
So how do you quantify the risk in terms of, did that feature in your PhD, or do you have to, so you said that there are 4 companies that plan routes, but then that's put you in a particular channel. Mm-hmm. So they're the ones taking on the risk as opposed to these companies that are suggesting routes, I guess.
Yes, so obviously all the routes that are flown have to have been okayed by NAV Canada, because they're the people who are going to be controlling that airspace and checking that everything's where it should be. So if there is suddenly a problem and something has to divert, they know where everything is. I think the interesting thing was that they wanted to take away the tracks. They were very keen on that. They didn't see it as a safety feature, and where they had a few track-free days, slightly due to COVID as well, because obviously there weren't so many planes in the air anyway, so they could take the tracks away with just a few flights and see what happened, and there were absolutely no problems at all. So because the flights can go so much closer together, you don't have a problem with flights not being able to all have the route they want, because they can fly pretty much the same route if they want to, as long as they're more than 3 kilometres apart, so they're not actually slipstreaming, then that's not an issue. So I think the fact that we're allowing more planes into the space means we're actually making things a lot more efficient. And the only reason they had to be so far apart before was because literally there was no radar across a massive box of the North Atlantic. So you flew in one end and there was like a straight line, and the air traffic controller would say that's where they're going to come out and it's going to be at this sort of time. And they didn't know anything that was going on in between. So the fact that they know I think it's every half a second, a message is sent from planes saying their position. So it's a whole different way of doing things. It's completely revolutionising safety, and the risk I don't think is actually getting any bigger, because there was more risk when people didn't know where the aircraft were. So the fact you've now got this 100% global coverage, you've got a lot less risk than you had before.
Does that mean there's a standard that NAT's used already, and was that a step change, or was it just a slow process? Because a lot of in aviation, everything's very standardized and has certifications. So this seems like very casual in some ways, like allowing aircraft to get closer to each other.
Over the last sort of few decades, every time there's been an improvement in the radar or the way aircraft can view each other, or the way that messages have come back to air traffic control, the planes have been moved a bit closer. So the tracks were much wider apart before they had some of the ADBS emitters, and they've gradually got slightly closer. This means they can come a lot closer, but that's why NATS wanted to do some of these experiments, just to see what might happen. And they did it when there were fewer planes, so it would be definitely safe. And what they found was it wasn't a problem at all.
Okay, I'm going to work my way around, 1, 2, and then 3. Just to remind everybody, this is pop star microphone time. Doing that doesn't work. So please point it at your mouth and you can speak into it. Thank you.
I have a question regarding the optimization methods that you guys are using for this research. I guess you mentioned about gradient descent method, but I think there are a few more, like Newton-Raphson and quasi-Newton. I think they're more efficient in some sense. So is there any particular reason behind choosing just gradient descent method over all these others?
So in the first bit of work, when we were looking at the time minimal and we were using the Euler forward step, the reason for that is that you're shooting off a lot of different routes, and then you're having to bisect the angle until you find the route that goes to the right place. So if you try to start putting in like a Runge-Kutta-4 in there, your problem is that it's actually taking too much time to do all the separate stages of the calculation. So computationally, it's not going to be very useful. So that was why we went with quite a simplified version. And again, in the Hamilton-Jacobi-Bellman, because you're doing so very many calculations, because for every set of grid points, you've got every set of every combination of controls. That means, again, that it was easier to use the interpolation using an Euler forward step, and it converges fast enough that it's not a problem. It's not going to make it massively more efficient to go for a Runge-Kutta-4, for example, because it's just going to take much longer. With the gradient descent method, we did use a Runge-Kutta-4, because at that point, it's not having to do as many iterations, so it's a slightly easier version. The problem with the gradient descent method, which we did through FMINCON, and the reason we went for that, it's kind of two methods, in fact. It's not just gradient descent. It tries the gradient descent, and then if it can't do that, it uses a region method as well. But the trust region method takes longer, but always gives you an answer. The gradient descent method might not give you an answer. So it tries gradient descent first, because it's quicker, and then it says, actually, we can't get an answer here, nothing's converging, so then it goes into the trust region method. And that meant that with FMINCON, you're getting basically the function saying, this looks like it might be a minimum. Here's a nice point, it looks like it might be a minimum. That's not great. With the Hamilton-Jacobi-Bellman, you're guaranteed a global minimum. With Pontryagin, you've got necessary but not sufficient terms in, so you know that you're going to get an optimal route if there is an optimal route. But when you look at the gradient descent, it may or may not be a global optimum. So what we then did with the FMINCON was actually encase it within a global search function, so that you're not just starting, we were having to start with, here's a vector of headings, here's a vector of airspeeds, work from here and tell me what the best possible result you can come up with is by changing these using gradient descent. If you give it different starting values, you could get different results. Not all days, but some days. In which case, having that encircling global search function just meant that it then goes through maybe 30,000 different iterations of your initial conditions. And so when you do get an answer back, it's pretty much likely to be a global minimum. It would be quite hard for it not to be at that point, but it doesn't have the mathematical rigor and robustness of Hamilton-Jacobi-Bellman. Thank you.
When you're optimizing, would the type of aircraft be significantly important?
Yeah, absolutely. It's really important that you put in the right aircraft parameters. So in the fuel burn, when you look at the fuel burn function, that eta 0 depends on all sorts of different parameters. And we had 9 different models of aircraft we were using when we looked at that data from flight radar data. So for every flight that was taken, for all those 3,100 flights, we paired up our simulation with the actual data, making sure it was the same aircraft we were flying. So our simulation used all the aircraft parameters for the fuel burn in exactly the same way that the actual flight would have run, because you've got to have like for like. And although the models of aircraft, it does make a difference, the sort of savings you get, it's not a massive difference between different models. I did have some nice graphs on a different thing, but I won't do it right now. But if you looked, there were 2 aircraft that looked like they weren't doing so well when you flew eastbound. Then when you flew westbound, they seemed to be much more efficient randomly. But then if you looked at the proportion of flights they were flying, they were much smaller than the proportion that other planes were flying. So basically, if an aircraft was flying enough, then it would average out the demands of the wind fields it was going through. But if it was only flying 1 or 2 flights, it was obviously going to have a lot more depending on what the airfield it met was, and what the wind field was that it was flying through. So we found that actually we couldn't say, oh, this is a much more efficient model of aircraft than that, necessarily from the data we had. What we could do was look more at the airlines, because it was a much fairer share of the number of flights.
But can I just add to that? is it the case that you could have some aircraft design types that would go particularly well into a headwind and some particularly well into a tailwind? Because that would make sense to me.
That would make sense, but that would be taken into account using the parameters, because the parameters do look at it, because the fuel burn function is actually based on physics. So it takes in all the information about the flights. Up until now, where people have been designing flight routes, they've used something called the base of aircraft data, the BARDA data, and that is just based on information that airlines have been giving into this database. What we try to do is use a more dynamic expression so that it's actually based on how the aircraft works. So it looks at things like the skin friction, the coefficient of skin friction across the wings. It looks at various different ratios of parts of the aircraft. And that's, if you're interested in finding out more about that, that's all in Paul and Schumann's work. They've got about 3 papers out now on it, and it goes through in massive detail all the different ways that comes about.
I think I will publish the references at the end on the mailing list so you can see them. I'll put those up as well.
Thanks.
If I understood you correctly, you were doing the bulk of your comparisons at a fixed altitude.
Yeah.
I think you mentioned 34,000. Obviously, you don't want more variables, I understand that, but over the course of a flight, an aircraft will be more efficient
if it comes
if it flies at a higher level, higher altitude. Yes. What odd observations have you got? Are there further studies?
This is very true. The altitude, when we first looked at this, we weren't sure whether to look at changing the heading angle and the altitude or the heading angle and the airspeed. It would be lovely to change all 3, and that's something I'm looking at the moment with there's a group from STFC who are looking at whether we can change the coding in order to be able to do that. Because obviously MATLAB doesn't want to know anymore, it's had its fill. But we could move into another language which would allow us a much bigger array size, and that would also allow for slightly more efficient work through the code, as long as we can get the same level of parallelization that we get in MATLAB. When you've got the altitude, we were looking at whether you get different winds at different altitudes as well, because that could also maybe be a reason for changing altitude. But it was really surprising that the winds are really, really similar at all the different sort of cruise altitudes. So we went from 400 HPA up to 150 HPA. And there was very little difference. The temperature field changed, but actually the effect the temperature has within the fuel burn is really minimal. The winds are much more important. And at all those different pressure levels, there was hardly any change to the wind field, which was quite surprising across that stretch of the North Atlantic. So the only reason we'd be changing altitude would be, as you say, as our mass drops, because we're burning fuel, it's more efficient for to make step climbs. And so that would be something that would be really nice to factor in. One reason why you might not want to do that is because if you plan your route at a fixed altitude and then part way across you maybe meet a supersaturated icy region, which is where if the plane flies through, it'll start making condensation trails, and those condensation trails or contrails become sometimes cirrus clouds, and that adds to the global warming effect massively. So you might want to avoid a supersaturated icy region, and those are much wider than they are deep. So then you could go above or below those because you wouldn't have factored in your altitude to the whole flight route. There are companies that are starting to try to use that optimal altitude, but it makes a very much less difference than changing the airspeed. So if you have to go for one or the other, the airspeed is really important. But if you have got the opportunity to put the altitude in, it might be worth doing. We did actually look at keeping the altitude the same for our simulation, but changing it, so allowing the aircraft that we were comparing with to change altitude, and we still made savings. Not as the same sort of level of savings here, but more than half of what we would be making if we kept the altitudes the same. So it's not making as much difference as you might expect not to do those step times.
Just coming back to the gentleman over here.
But as I understand it, airplanes fly in different directions at different altitudes so they don't bump into each other. If you start changing, you've got different aircraft going in different directions at different altitudes, they're going to bump into each other.
It depends what your plan is before you start. I think air traffic control would have to look at your plan. So you could give them an optimised altitude plan and just see what they decided. If you wanted to change because you hit convection or a supersaturated icy region, you'd obviously have to ask their permission. As you do for a step climb now, you have to ask if you go up or down. What you find with the tracks at the moment is it's actually different times of day that you fly one way and then fly back the other way. So all planes have to have got to a certain position by a certain time and before the tracks open in the opposite direction. So they tend to do that using not the altitude as much as the timing. And in fact, with planes flying closer together, again, you wouldn't have to have the different altitudes because planes could fly all at the same altitude if they wanted to. And the tracks are actually optimised for a 250 HPA, so 34,000 feet, roughly. So that tends to be what they've looked at so far. There was a study that Irvine and Shine did, which looked at what happens if we go at 200 HPA, what happens if we go at 300 HPA, and they found that it was a negligible difference between the 250 and the other two altitudes.
You'd have to have every aircraft and association in the world coordinating so that every aircraft was known, so that they didn't.
Yeah,
they were all playing the same game.
I think what you got to think in terms of is separate airspaces to some extent. So across the North Atlantic, you have planes going one way, planes going the other way. There's not a lot of planes going up and down. When you start looking at other airspaces, so if you start looking at the Single European Sky project, they're looking very much at trying to open up the whole sky over Europe so that there aren't any restrictions. So that includes using airspace that's been used for military purposes previously, so actually sharing military and civilian airspace. And they are very much looking at, right, let's look at all the flights that are happening during a day and let's plan everything out. Because it's not actually as difficult as it might sound to do that. I think as long as people have enough notice of where planes are going, then you can actually put that into the equations that you're using. This is particularly, the method we were using is particularly good for across the North Atlantic because we're not having to worry about the winds changing due to geographical features. So we haven't got the orography to deal with, we haven't got problems with flying over land and buildings and all the other things that make changes to the weather patterns. We've got a nice, slowly evolving wind field, which is why across the North Atlantic is a particularly good place to change things. If you look at the Pacific, I did some work looking at some flights over the Pacific for some people who were looking at volcanic ash clouds. And actually, you're not making the same sort of savings because you don't have that same predominant eastbound jet stream that you're working with. It's a little bit different the way the weather tends to be. So you could make routes going anywhere, but I think this is a particularly good area for making carbon dioxide savings.
Lots of thoughts in my head. I was just thinking volcanoes actually when you were talking about ice clouds, because that obviously causes. A couple of things have come in on the chat. So one of them is, what made you decide to do this? What made you think of this project?
Okay, so I was part of the Mathematics of Planet Earth Centre for Doctoral Training at Reading University and Imperial College, so it was a joint group. And Professor Paul Williams, who's at Reading, had started looking at some of these time minimal flights. He mainly works in turbulence, but he was really interested in the time minimal flights, and he wanted to see whether there was something we could do along those lines. So I was very interested in all the different professors had to give a pitch of their particular project, and this was the one that I really thought was very interesting and actually really applicable, because I was very keen to spend my time doing something that might get used at the end of my 3 years rather than seeing it put in a book and never looked at again. So.
And just to make it clear, so your team won a prize for this, and this is being put into action now, is that right?
So what happened was that Nats were able to run their experiments by citing the fact that we'd shown that the proof of concept was there. And that then obviously it means that it's had quite a big impact. And I think that's why the Times Higher Education Award was given to the project.
Very nice. Okay, so then there was also, I'm going to jump to one which was very appropriate for what was just asked. So do you have equivalent research yet on long haul to Australia or New Zealand from the UK? And what changes might be necessary to allow flights between these locations, presumably meaning for them to be optimised?
Yeah, so if you're looking at a flight that's going from Europe across to somewhere like Australia, I know there are some really long routes that people are bringing in now that they want to try and do in one hit rather than having stopovers. And that would be quite a nice route to try and optimise. But again, you are going to have the issues of airspace and the fact that you're flying over land some of the time. So that will change a little bit the way that you work. The equations will still work. It's whether the wind field is predictable enough to make it worthwhile.
Could you change the time step? Would that be relevant or not?
You can change the time step. Changing the time step's not necessarily relevant. If it depends. With the transatlantic, you can use a daily average because the wind isn't changing very much. If you start going to somewhere where the wind is changing more, and you're actually changing your wind field as you go, so you have an evolving wind field rather than a deterministic wind field, then I guess you can factor in everything that's happening, but it's going to be very, very computationally expensive.
Anybody else in the room? Okay, so the other thing I was wondering is there anything else that your approach doing this with flights could be almost directly applied to? Are there any other offshoots you're considering?
Well, the Zermelo equations originally were to do with boats, and so there is potential for looking at boats as well, but obviously you then have to factor in various different currents that you're coming up against, so it's a little bit more complicated when you start looking at boating weather and the sort of sea interface with the air. It's not quite as straightforward as just having the winds in the sky, but yeah, that is one area you could look at. What's quite useful at the moment is that a lot of people are looking at drone flights, and so it could be applied to drone flights. There's a lot of material out there trying to get efficient drone flights, but also drone flights where if you're having something delivered, it actually gets to you, which is always better. So I think certainly the Met Office are looking at opening a whole department just for drone flight routing and weather. So that's one particular area.
You've become quite an expert on flights and how they're managed, and you were just saying completely unconcernedly that the skies over Europe, they're looking to open them up, and that commercial and military aircraft might share space. Should we all be scared or not?
Not at all, because we know where everything is, and I think if it works properly, because everyone files their flight plans properly, which they'll have to, then it shouldn't be any different from just having commercial and commercial. I think with the military, there's probably less military action over the main areas that you want to fly over anyway. And if you're thinking of flying to Europe, you could take a train. So maybe take a train for a bit.
And have you flown a lot since you started this work?
I have actually not set foot in an aeroplane since I started this work. We started the work bringing in the data, and I was still collecting in the data, and we started on the 1st of December 2019, and I was collecting it quite happily. We got through to February, and my supervisor said, should we go through to March? And I said, maybe not, just as COVID grounded all the flights. So it was actually the perfect timing to go from the 1st of December to the 29th of February and not sort of carry on through from that. But I actually haven't been up in a plane since then, because if I go anywhere in Europe, I will take a train. So I've been to conferences in Spain and in Vienna and in Germany, and I've trained to all of them.
I suppose if you're working for a climate institute, then that's very... What's next for you?
So there is some talk of, as we said, about trying to optimize the code a little bit and maybe changing coding language so that we can put in a few more states or some more controls and just see what happens. But that's sort of a side project, because at the moment I'm working for the Walker Institute at the University of Reading, where we're looking at adaptation policies. So it's all to do with climate change adaptation. And the idea is that we use interdisciplinary research and pull in everyone's different expertise, whether they are an expert in soil or in crop growth or in hydrology. And we pull all that together to try to work with different countries, mainly in the global south, who need a bit of a hand working out their national adaptation policies and making sure that what they're suggesting is covering all the uncertainty that's inherent in the different climate projections. So obviously when you start projecting climates up to 2100, you have a load of different models. So there's an ensemble of 31 different models maybe you're looking at, and within that you've got lots of different scenarios and lots of different carbon pathways. So depending on what everyone down here does, that's going to change what happens in the atmosphere. All of that, and every single different model run will have a certain level of uncertainty as well. That brings out massive uncertainties. And then if you say to someone, okay, here's a load of data, now adapt your country so that you don't have any problems with climate impacts, how are they going to do that? They're sort of paralyzed by having too much information. So what we're doing is translate it into storylines. So by having a climate storyline, you say, okay, looking at the data, let's imagine the future, and this is what we think is going to happen. Or here's another story of what could happen, or here's another story of what could happen. And then let's find an adaptation route which will allow us to adapt successfully for all of those stories, so we don't risk any maladaptation. Because sometimes what happens when people put a lot of money into infrastructure, for example, they then find that there's a backlash from that if a different climate future happens. So there are sometimes floodings caused by the fact that people are trying to harvest water because they thought there was going to be a drought. So trying to incorporate all of that uncertainty into a sort of hazard analysis is what we're looking at. So we're looking at new ways of calculating climate risk, using these storylines, and then helping people to adapt so we've got the top-down climate projections that people have used in the past, but then we're using bottom-up stakeholder information so that each community can say, if this particular hazard happens, okay, the impact's going to be different depending on the vulnerabilities of the people who are there, depending on the exposure of different groups and different infrastructure, and depending on the resilience, how quickly they can bounce back before the next impact happens. So we're putting all that together, and I've been working with Pakistan quite a lot over the last few months, and I've just moved on to a project with Iraq, and also looking at a transboundary project where we discuss things. It's an interesting part of the world, but it's looking at Syria, Turkey, Iraq, and Jordan, and looking at whether they can actually work together across that boundary to be able to help to fight the sort of climate impacts that are likely to happen.
Do you want to take us through your slides for that?
I don't know if people want to. Do you want to see the slides?
I'm thinking I was like, you can't.
And then just see slides. Okay, cool. Okay, so this will kind of take you through a bit of what I'm doing with the Walker Institute. So we're really looking at trying to help development so that it becomes climate resilient development. Ooh.
Just give me a second.
It's okay. Okay, so we're trying to make some of the communities that are trying to develop able to do that in a climate resilient way, because it's a good opportunity to actually put in that climate resilience on the way through, rather than where we've already got a developed society here, it's much harder to try and alter things. We're looking at some of the low-income countries because their vulnerabilities to climate hazards are much greater. Working with not just the governments, but also some of the academics in the countries, some of the non-governmental organisations as well, and focusing on lots of different areas. So looking at food, looking at water resources, looking at gender, that's really important, looking at health. And our projects, as I say, are mainly in the global south. We've got one coming on in Laos quite soon as well. The odd thing in England, we've been working with, we work with Scottish Heritage a bit, and then we're coming onto a project with the National Trust as well, because they're worried about some of their areas drying out, where they've got underground areas of interest. But the main method that we're looking at is trying to match both having some literature review, but also having the stakeholder consultation, and then feeding in to work out what our project's going to be about, whether we can use some climate modelling, so we might go from a global climate model down to a regional climate model, what our projections are, and then including all of this information into those storylines, so that we then can try and assess what risk there is, but also capacity build within country, so that once we've done this, we can talk to people within the country and we can show them how they can do it, so that if we do it for a whole country, maybe they want to look at just little areas or even go down to district level. And the sort of idea behind the risk assessment is that we look at a hazard, but it's not all about how bad the hazard is, because it depends on how many people there are, what sort of infrastructure there is. It depends on how quickly they can bounce back, as we said, and it depends on what sort of vulnerability they have to that climate hazard. So a hazard will not have the same impact depending on where and when it happens. So when we develop the climate storylines, we're looking at, this is some disaster data on Pakistan, looking at the different disasters that have hit over the last 30 years, and also how these kind of intersect with the different provinces. So are there some climate disasters that have hit all 4 provinces? Are there particular provinces which have more disasters than others? And why is that? And then looking at some evidence, so current evidence based on thousands of people who've been affected by droughts already, or it might just be data on the population density, or the level of poverty in a particular place, or the level of literacy in a particular place, because all of those add up to the vulnerability. And then we also look at the climate future projections. So we're trying to include different models, different futures and different seasons, so that we can include all of that uncertainty and not just average it out, which is what tends to happen at the moment. And that means we can create a nice infographic which tells us the story and says, this is what's going to be happening, this is what you need to look at, and that's accessible to all the different stakeholders. And from there, you can look at what the socio-economic impacts might be and where you can maybe make changes in your adaptation. So that's, in a nutshell, what I've been doing recently.
Thank you. I noticed on your map, I'm particularly interested in places that I've been lucky enough to go to, which are threatened island nations. So there isn't a star on the Maldives down there. They're in a lot of danger, aren't they? And what about the island nations? Are they just not getting any kind of interest in this?
What we've been doing is we've actually gone through the United Nations Environment Programme. So we have a contract with them, and whenever we actually work in the South Asia Pacific region, and whenever a country says to UNEP, we need some help with this, then we're brought in to support that project.
Thank you. It's amazing how many different places you're working with, and the variety as well. I mean, some of them, as you say, with floods, and others with drought and
actually floods and drought.
Yeah.
I mean, if we look at Pakistan and Iraq, their problems are floods and droughts.
And an underlying pretty much at least one avalanche or earthquake every year from the looks of it as well, which doesn't help.
We tend to be looking more at the climate change issues, and earthquakes, there've been some research into it, and climate change is not causing more earthquakes. If you have a drought condition, then it can cause very low level earthquakes to happen in a more likely way, but not a major earthquake. So actually the research shows that we don't have to consider the earthquakes in the same way, because we're just looking at what's going to be exacerbated by climate change, really. So things like sandstorms, dust storms, definitely. Landslides, avalanches, yes. Flooding. Sometimes we're also looking at things like the pests that are landing on the fields, because that, again, climate change will encourage the numbers of pests in certain places, and health issues as well. But we're not really looking then at earthquakes.
Good to know. Lovely. I think unless anybody has anything else urgent. Lovely. In that case, I think we're going to wind it up. Just to say before I say a proper thank you that we're going to carry on in this hybrid format. And again, anybody who wants to come in on Zoom call should make sure that they're part of our mailing list on the day before 2 p.m. They can always take themselves off it again. You can add yourself or remove yourself from our mailing list any time. Doesn't need me to do it. Instructions are on the website. Also to say that I'd be interested in feedback on the slight readjustment we did of this room. It's slightly different, so it's good to know. Hopefully we'll carry on being able to get printouts onto the tables, especially as the light is, I think, going to get worse in the summer, because we don't have blinds here, and it's one problem is we can't make it completely blacked out. Looking ahead, we're carrying on the second Tuesday of every month, except for August. So I have a very scientifically minded chiropractor to come and talk about the science of our muscles, bones and alignment at some point. He's my own chiropractor and is very, very good indeed. That, I think, will either be April or June. And also in May, we've got somebody who the very, very older regulars may just remember from a very long time ago, about our third or fourth year, who is an agrochemist coming to talk about the kind of past and future of farming and what's been changing about chemicals used on crops, about non-chemicals, about different ways of making sure yields are improved in order to help out countries that are having difficulties, what Britain may have to do about its farming. And I think that will probably be the May one. So the second Tuesday of every month carrying on. Thank you as usual to Pharmacology for hosting this, which is amazing, and particularly to the night receptionists, Graham, who's on tonight, and James, who's the other guy who helps out, and they're just fantastically supportive. My thanks particularly to people helping, so tonight Leo and Nicholas, which is really amazing. And thank you for everybody for coming into the room, and for the people online. Biggest thank you of all, please, Dr. Cathy Wells. Brilliant. We're going to do a bit of dashing around. Please talk to Cathy if you want to, because we're going to